Hi guys, this is Mr. Kolpak. This is a sort of virtual lecture for our current unit. We're going to be talking about some things about the solar system. How to find planets in the night sky. Where did the solar system come from? And what the heck is the snow line? There's also a surprise visit to the Natural History Museum buried in here somewhere. Alright, so how would you find a planet in the night sky? How would you know the difference between a planet and a star? Well, the first thing is that planets don't twinkle. Do you know what twinkle is? Twinkle, twinkle, little star. You know how sometimes the stars seem to flicker? Well, planets don't do that. So that's one thing you can look for. But there are some other things too. They tend to be the brightest things in the sky. Because they're so much closer than stars being incredibly far away, even though they're very much smaller than stars, they look brighter than most of the stars, especially the planets Venus, Mars, Jupiter, and Saturn, which are some of the brightest objects in the sky. If you watch them night after night, they will change their positions. This is where their name, planetes, comes from. It means wanderers in Greek. And so if you see a star that doesn't stay in the same fixed pattern as the others, then it is a planet, not a star. They often change their brightness as they get closer to us and further away from us. We see their brightness change significantly. So that's usually a clue that it's a planet, although some stars also change in brightness. And if you looked at them through a telescope, you would see that they're not just a dot, as a star would appear to be because of its great distance, but instead you would see them as a small disk. Maybe some colors and some patterns would appear as well. Finally, planets all appear more or less on the same line in the sky. Of course, the planets of our solar system are in a plane, a two-dimensional plane like a table or like a CD. But to us in the sky, that appears to be a line. This plane is known as the ecliptic plane. Here's an example of what that looks like. You can see the planets labeled there and how they all kind of form a line as if they're pearls on a pearl necklace. And this line is the plane in which our planets circle the sun, and as it's projected in our sky, we see a line. See this from an outer perspective, we would see the solar system like this. The sun being in the middle and these colorful Alright, so the age of the solar system, we've heard about radiometric dating before. And the age of the solar system that scientists believe in is based on the same technique of counting up the amount of various radioactive isotopes. Typically, uranium and lead are used for this because of their very long half-life. And based on this, we've looked at some very, very old rocks on Earth. The oldest rocks on Earth are about 4 billion years old. So the question is the Earth's age 4 billion years? And if it is that the same as the solar system's age? Did the Earth form at the same time as the rest of the solar system, all the other planets and the sun? And then there's a problem with looking at the age of rocks on Earth, and that is that rocks on Earth get recycled, as you know, by plate tectonics. They get melted and reformed. And when that happens, the isotope ratios are going to reset. So the Earth may not be the best place to look for the oldest possible rocks in the solar system. So in fact, we've found rocks on the moon and in meteorites that have fallen to Earth that are older than the oldest rocks we found on Earth. We don't think there's any plate tectonics happening on the moon, and meteors that become meteorites are very, very old indeed and have, we don't think, changed at all since the very beginning of our solar system. So, in the end, we think the solar system is 4.5 billion years old, and that's based on radiometric dating of old Earth rocks and of moon rocks and meteorites. So how did all this happen? How did the solar system form? So this cartoon is an attempt to describe that in a visual way. The first image that looks like a ball with the arrows pushing in, that is actually much bigger in scale than any of the others. It's not easy to tell that from this drawing. But there was some sort of giant cloud of gas, and part of it became denser than the rest. And that dense region started to collapse under its own gravity, and that's what that first cartoon frame is supposed to show. Okay, in the second frame, we see that the ball of gas has turned into a disk. Now the reason for that is that any cloud of gas is likely to be spinning in some direction or another, if only a very small amount. It's just randomly placed things in space are going to be spinning a tiny bit at least in some direction. It's just sort of, on average, that's going to happen. And because of that, as this thing shrinks under its own gravity, whichever direction it had started spinning in, it spins faster and faster in that direction as it contracts. This is called the conservation of angular momentum, and it's the same thing that causes an ice skater or a dancer, as they pull their arms in closer to them on a spin, to speed up. So the matter in this ball was collapsing, but because of the spinning that became faster and faster in a particular direction, it was not able to collapse in that direction, and so it stayed spread out in that plane, which would eventually become the ecliptic plane of our solar system, and it formed a disk. And that's what we see in frame 2. In frames 3 and frames 4, we see the gunk, the dust and gas in this disk, accreting or collecting into clumps. Some clumps of dust, some pieces of dust and gas are going to start bumping into each other, and things are going to start to grow because of gravity, and whichever objects are the biggest are going to accrete more and more matter. There are going to be all sorts of terrible collisions between these early clumps of gas and dust, but some of them are going to survive these collisions. These clumps of gas and dust that grew and swept their orbits clean ended up becoming the planets. Now this is, of course, just a theory. No one was around to see it. We don't have super direct evidence of it, but it does explain a lot about our solar system. For example, it explains why all the objects in the solar system tend to rotate and revolve in the same direction. All the planets and the Sun, apart from Venus and Uranus, rotate and revolve in the same direction. So of course you wonder, well, what happened to Venus and Uranus? And the best theory we have for that is sometime in their early childhood, you could say, they got whacked by something pretty big in this process of accretion, and that disturbed their original angular momentum and caused them to spin the other way. But apart from that, the conservation of angular momentum of our initial solar nebula, we think, is responsible for the rotation and revolution we see today.